spans an incredible range of length and timescales where he routinely uses machine learning, quantum chemistry, and automation. The title of Alán's talk is Self-Driving Laboratories for Organic Molecular Design. And with that, Alán, I'll hand the floor over to you.
Well, thank you, Tom. Although I've been very busy doing a lot of work this week and missing the talks, had Gabe Gomez here as my spy, getting text and screenshots about all the talks. So I've been a spy listening to everybody, and it seems that this symposium has been excellent. So let me just talk about my research as it connects to the screenshots and talks that I heard through Gabe. And I'm happy to end it and hopefully connect some of the dots that I saw people were talking about. So I think what is really great about the lineup of speakers and topics in this symposium is that I think we're all aligned on this goal. Would I like to say there is no time for science as usual? Outside of my window, I don't know what's happening here, right? Yeah. Outside of my window, here in Toronto, there's a smoke. There's like a lot of fires in Ontario, right? Because of climate change. So we need to actually work and solve those problems by accelerating discovery of molecules and materials. And I think that's the importance of transforming our chemical industry to a fast discovery industry rather than a slow industry. So before I begin the scientific content of my talk, I want to make 3 announcements of 3 organizations that are relevant to this general field. And because we're talking about a field in this symposium, let me just make 3 announcements related to it. The first one is a journal, okay? We are open for submission very soon, in about a couple of weeks. A new journal, Gold Open Access Journal from the Royal Society of Chemistry called Digital Discovery. I moved from Associate Editor of Chemical Science to become Editor-in-Chief. We're about to announce all our editors and board extremely soon. It's being formed on the fly, and maybe some of the people in this symposium are actually getting invitations to be part of the board as we speak. So it's a very exciting time, and I really welcome people to start sending us your papers. It's going to be a very data-driven journal. We're going to be very interested in your data and your codes. And it's about this symposium, right? It's going to be about AI. It's going to be about automation. It's going to be about accelerated discovery. So hopefully this journal, and remember it's Gold Open Access for the first couple of years, is going to be a good destination for your best papers, okay? Second announcement is we did launch at Toronto a consortium. We call it the Acceleration Consortium. That is a university initiative with a very global vision of transforming molecular materials innovation, again, with the same idea of using AI and automation. What is unique about it, and that's the reason it's not called an institute, is that since the very beginning, we are inviting companies and startups and a lot of international groups to participate. So if you as a faculty, as a research lab, or as an industrial member want to know more, please send an email to Aspuru@accelerationconsortium.ai or send us a DM in Twitter, and we'll be very glad to answer your questions about the Acceleration Consortium. And finally, a quick plug to the company I founded 3 years ago, exactly on this topic, called Robotics, which it's doing really well. You can see there a screenshot of a lot of the products that we offer to our customers, kind of in a very, very, I would say, professional way. They are kind of like not academic codes like mine, but they are real production level tools. And as a matter of fact, to program manage one of these tools, we were able to snatch one of the very important members of our community, Marshall Brennan, which I'm welcoming here publicly to Robotics. And if you are very talented, PhD, recent graduate or postdoc, and are interested in accelerating discovery of molecules and materials, please send us your CV at Robotics. We are growing, and basically we're trying to be the first chemical company that accelerates discovery top bottom, you know, basically having this at the center and then producing chemicals. Okay, so those are the 3 advertisements that I wanted to make, and now I'm gonna hop into again the main goal. So just remember what happened with COVID, okay? It is incredible that even though there was a pre-discovery effort for Moderna of a couple decades, Moderna had a tool that was able to not only discover but scale the production of a vaccine that went into my arms and the arms of about 1 billion people in the world already in a year. Just think about that, okay? And then if I were to tell you that the solution to COVID was a molecular material, it's not necessarily clear we'll be able to do the whole discovery process in a year. And that's what we're trying to do, right? In this Acceleration Consortium, Robotics, the Journal Data Discovery, the research groups of the many people in this symposium, the centers such as the Molecular Maker Institute, etc., all around the world, is this idea, right? This idea, what is different about what we've been doing science as usual, is that really needs to break the barriers between what is a theoretical chemist, what is a physical chemist, what is an organic chemist, what is a computer scientist. Just today in Facebook, eating lunch before even starting to connect to this symposium really quickly, I saw that Max Welling, if people don't know who Max Welling is one of the 4 or 5 top figures in AI in the world, okay? Max Welling just announced in Facebook just today, I was just, wow. He's starting a lab funded by Microsoft Research in Amsterdam for using AI for molecular discovery. This is how interesting the world is happening. Okay, now Microsoft making a bet around Max Welling, which is again one of the top 5-10 figures in AI in our field. So that means the people in the field of AI are entering in droves here, and it's very important to welcome them and interact with them. Okay, enough of the general picture. What is a self-driving lab? How is different to high throughput virtual screening or high throughput screening in general, experimentally? Well, the idea of a self-driving lab is that you're going to use the typical good and old high throughput screening equipment, and you're going to couple it to high throughput characterization equipment. And I agree with Anat's previous talk that it's not necessarily true that you need tons of data to be dangerous, and actually also agree with her that chemical intuition is crucial. So all of these points are extremely valid. And having said so, the more data that you have and the more integrated the AI is with experiments, the faster you can drive the experiment. So it's quite interesting that the interface to the ChemSpeed that we have, also she mentioned ChemSpeed before, is pretty much a row-driven interface where you provide a list of experiments are done, and the list comes back. You know, it's really not as interactive as it should be in terms of being able to interact with an API and actually drive the experiments as they happen, right? So that's the difference, okay? So self-driving lab is a lab that takes data, probably less data than a super blind high throughput experimentation, and optimizes such an experimentation as it goes. And I'll show you some mathematical examples of how that looks like. So again, with a lot of, hype comes up recognition. So MIT Technology Review recognized this field, the field that we're on, AI discovered molecules, all collectively, as one of the tech breakthrough technologies 2020. So we as a community need to deliver, otherwise we're going to be in trouble. I feel partially responsible because I am associated with the institutions that you see there, Robotics, University of Toronto, Vector Institute, and also collaborated with in Silicon Medicine. I'll mention that in a slide if I have time. But I'm going to skip generative models and talk about them at the end only if I have time. So let me just tell you about the materials that I'll be telling you today about, just the basic photophysics that we need to understand what I'm after. And then I will show them as an example of this self-driving lab target. So we need to have a target. The target that I'm mostly interested about is light emitters. So let's remember a little bit about the photophysics of light emitters, like the ones in your cell phone, okay? So your traditional garden variety organic molecule will actually have a triplet that is called a triplet because it's 3 energy levels. 75% of the excitations will fall into the triplet manifold. That non-radiative will be the case into the ground state. That means that if you want to emit light, 75% of your light will convert into heat. Okay, if you have electron carriers that come from electrodes, they recombine in your molecule and try to be emitted. Only those in the singlet will fluoresce. It's funny that how still the blue in some of your devices uses this technology because blue subpixels are actually stable. Okay, there are molecules you can find that are stable, and all this triplet energy is lost. Having said so, of course, many people have been made rich, and a lot of technology has happened because people realize that if you use transition methods, you have intersystem crossing enabled by the mixing of the singlet and the triplet due to relativistic effects. And now phosphorescence is fast, and you are able to emit the light from the triplets. But organometallic bonds are very feeble, especially in the excited state, and therefore these molecules break apart. They don't work for the blue ranges of the spectrum. This is where Chihaya Adachi, one of my heroes, he started a technology called temperature-assisted delayed fluorescence, where molecules that have a very small gap still able to thermally assisted reverse system crossing, go back to the singlet and emit, were discovered. They were very rare, and therefore one of the earliest applications of AI for chemistry that I know in terms of high throughput screening was this paper led by Rafa in my group. Rafa is now a professor at MIT, where we built a library of about 1 million molecules, calculated about 100,000 of them, used neural networks to predict the rest, built a tool called Molecular Tinder for voting, down selecting, and making 40 devices, out of which 3 of them were champion candidates. The reason I always like to mention this in my talks is because this is a strawman that I'm always trying to fight against. I mean, I could have been proud 5 years ago and said this was victory, but it was not victory because we only were able to make 40 devices out of millions of molecules that you can compute or you can screen computationally. And that bottleneck led my lab to move into experiments when I moved to Toronto from Harvard in 2018. And now I have an experimental subgroup to try to realize the idea of accelerating the synthesis and characterization. So it was around that time that we decided to go to a workshop. Many of the people in this room were in this virtual room, were in that workshop in Mexico City. What a wonderful time was that. We wrote this report with Christine Persson and myself as co-leads, and of course with 50 or more other scientists around the world, about this incorporation of data and orchestration and robotics, and we call them materials acceleration platforms. There are several papers that touch on that topic, some of them in Trends in Chemistry, that will make the organizer of this symposium very happy. But you can read about them over here or read the original report. So today I'll tell you about the material acceleration platforms that we are building under my collaboration with some of the speakers in this symposium, Marty, Bork, Lee Cronin, Bartosz, and Jason, right? So I got together with the 4 of them and me as the 5th one, as the main PI. We assembled this project that, of course, you heard them speak already, is aptly named Madness, due to the madness of the collaborators, but also the madness of the goal, which is try to integrate the different architectures that each one of us has in our labs, the different software tools that we have, in a coherent main mission of accelerating the discovery of organic emitters. Okay, but which type of organic emitter, you might ask, is the one that ultimately we're after? I remember in the beginning of my talk, I told you we wanted to accelerate the discovery of a material from 10 years to 1 and commercialization. So for that, you want to pick a material that has not been really commercialized, it's barely discovered. So in 2017, when I started designing my lab before moving, Chihaya Adachi, again, had reported that he was able to get fairly long-lived solid-state organic lasers. Now he's founding a company called Koala around this technology. I've seen their technology, it's extremely impressive. So it is very possible that we're going to have the next generation technology in your cell phones. We'll use some sort of coherent emitter, for example, for measuring your face and other things like that from plastic. But there's very, very few molecules, tens of them, that work very well in the organic solid state. So that's a very good target. Now, a topic to raise in this symposium is obviously 1 year, it's already passed and gone since 2017 or 2018, right? When I'm telling you all of this. It takes a long time to design, build, test, scale these materials acceleration platforms. So something I've been thinking a lot about is that we need to build many of them collectively to lower the learning curve, right? The learning curve means the more you build, the faster you make them, the cheaper they are, right? That's a very, very simple concept in economics. We all together need to work in building many acceleration platforms in Anat's lab, Lee's lab, Marty's lab, etc., so that we can collectively lower the cost and the complexity to make these things more and more useful. But I'm happy to show you results from the one in my lab. And again, it's perhaps not news to the audience in this symposium, but I'll spend some time discussing new research in my lab on this topic. is the idea of iterative coupling schemes, right? How can you take what nature does, progressive protection, the protection type schemes, or progressive building block building, which is basically what is the technology behind peptide, nucleoside, saccharide synthesis that has basically, in my opinion, enabled the data science-driven nature of biology, right? Why? Because they have robust reactions where they can order DNA strands, they can order protein strands, they can order sugars, right? Almost, I even have seen, how do you call it, dispenser machines for polynucleotides. So the question I have is, can we do that for organic chemistry? And of course, the thesis is following the leadership of Marty Burke that has shown that with very few reactions, and potentially even one is even controversial, right? We will be able to access huge swaths of chemical space, right? And this is just the example of the middle boronate protected Suzuki coupling. We heard in the previous talk, beautiful work about the boronate aspect of this reaction. I'll be telling you a little bit about the phosphine aspect of this reaction and mechanistic aspects. But if you even think about the simple carbon-carbon coupling, but you could also, of course, think of carbon-nitrogen coupling and other very basic reactions, at the expense of having complex fragments, you might be able to access a lot of functional space. And there's a lot of degeneracy in functional space. That means many molecules can be functional that solve a problem. Therefore, reaching the entire chemical space might not be as necessary. So now the topic that we wanted to attack, this topic of organic lasers, requires understanding the photophysics. Okay, so here we have an advantage over the drug discovery folks, because we can actually have a lot of the characterization in-house, and also the functionality is pretty well understood. We don't have to bind to something. In this particular case, yes, the molecule is in a host matrix that you need to organize its energy levels and its properties, but you can think about as a necessary but not sufficient condition that the photophysics of the molecule is right. And basically, the modeling that you need to think about is reducing all the parasitic processes that you don't want, like non-radiative decay, intersystem crossing into the triplet, so you can have triplet absorption or absorption into excited state singlets, etc. So all of these processes can be modeled by these parabolas, right? I'll show you later, right? These parabolas that you can displace, and you can run pad integral calculations and calculate the spectra and the transition rates. This is just traditional physical organic chemistry, computational type that you can high throughputize. But what is interesting about the approach in madness is that we don't want to do a lot of retrosynthesis. Even though I just show you Kevotics as products, Kevotics has, we believe it's the world-leading retrosynthesis AI software. You can talk to Kevotics more about it, actually. We're pretty bullish about it. It's called Reaction Sage. But, there's a lot of AI for retrosynthesis, but here we're talking about AI for forward synthesis, right? Taking blocks, using a generator to actually build a chemical space that is accessible by the robot. Okay, for that we use the AI and the handcrafted models that Bartosz Rybowski talked to you about. So we use Bartosz's technology from his company Alchemy to build and prune the molecular library in terms of chemical reactivity. Okay, from that, then Cyril Lavin in my lab and others lead a quantum chemistry screening project where we actually look at the promising targets of this about 100 million molecular library that is reachable by the robot, and then do slow screening, about 15 experiments per day when you are in full production mode, and we're not in full production mode yet. We have done many hero runs, but not full production mode. It will be about 15, 30 molecules a day in the chem speed. So what is the type of photophysical information that you need? For example, in this case, you see this predicted baryonic resolved absorption and emission spectra. It is very important to minimize the overlap between the absorption and emission spectra for having a good laser, for not having reabsorption in the laser. So we do that by, for those computational chemistry aficionados, by using traditional density functional theory with gradients and Hessians and displacements, pad integrals on top of it, that will take about 15 hours per molecule, roughly, right? But you can reduce it to 15 minutes if you use the right semi-empirical methods. And then you can obviously upscale or verify your molecules with the high throughput approach. So that has to inform your model. So this is kind of where, if you were in pharma, you will think about ADMET and toxicology and other properties and crossing barriers. Here we want to think about the photophysics of a device. You want to maximize gain and minimize loss. You see all these rates in this quantum master equation that you need to maximize and minimize. But if you rationalize what your molecule needs to do with respect to this photophysics, then it's pretty clear what a good molecule would be for an organic laser. Okay. So now we go into the iterative cross-coupling, and many of my collaborators might have mentioned to you some of this. Today, I will focus mostly on what happens in my lab, but needless to say, I'm extremely proud that postdoc in my lab, Han Hao, has reproduced a modern version. This is an old picture, but a modern version of this batch synthesizer of Marty Burke. My lab can reproduce the technology of Marty, and we can use it as of today. My colleague, Jason Hein, has reproduced the computer from Lee Cronin in Vancouver. And I loaned my computer to Jason, but hopefully Jason will send it back soon, pre-assembled. And hopefully my lab will also have one of those famous computers. We have used, of course, this N9 robots from Vancouver together with Jason. But today I will tell you about our more traditional use of the ChemSpeed, which we had to modify and adapt its workflows to be able to do this type of reactions. So this is a traditional boron-amida protected, Suzuki coupling with halides. A lot of work that is not going to be shown in slides here, but it's about to be submitted to journals, has done on the optimization of general reaction conditions. This is led by Marty and Bartosz. Also, property-driven optimizations we also have done. But in general, I would say the robot that has been able to do this much more productively at the moment is Marty Burke's robot. It's actually running this thing continuously. Okay, so my lab, on the other hand, being built during COVID, is getting there in terms of productivity, but it has the advantage of having ultra-fast time-resolved lasers in the back, coupled to the HPLC, coupled to the ChemSpeed. So this is the general scheme of our laboratory. This is, if you haven't seen them before, this is how these ChemSpeeds look like. We have we can do about 16 reactions in parallel. We have a solid dispenser, kind of one of the most finicky pieces of this equipment. And we can also, of course, now also use pre-prepared solutions outside with other balances as well to compensate. And then, of course, we can actually do reactions in inert gas atmosphere, which is important for these conditions. So that's kind of what the robot does. And this is just a typical eye candy of any automation chemist. But there's a lot of work that has to be done on the back end to actually integrate this machinery to characterization equipment. And this is where Kazuhiro Hotta, Tony Gu, Martin Seyfried, and many others in my lab spent a lot of time building the pump systems that connect the ChemSpeed back to the HPLC, where you can actually, because you know what reaction you did, you can pretty much infer what are the different fractions corresponding to. You can separate the fractions and then rerun again, separate the fraction that you want, use an automated diluter, and send it to the ultra-fast system. So here, not shown in the right, is actually 2 tabletop lasers that we have for doing steady-state absorption. But you can see here the simple photolysis lifetime, which we have them almost in 3D. These laser boxes are kind of in this 3D, in this optical table. And you can see barely all this little tubing here that is all automated with our software to dilute and then inject. And therefore, it is possible now to synthesize, separate, and test all in flow in my lab. In some sense, it's an organic chemistry lab, an analytical chemistry lab, and a laser lab run by a theoretical chemist. So that's why it's a little bit madness, okay? But you can see here in line a prototypical organic laser with the absorption and emission lines, very little overlap, and also a time-resolved ultra-fast experiment done on the product of the organic reaction. So this is a traditional kind of, make, test, design, analyze in a tabletop, right? So this is what was happening in the lab maybe almost a year ago. For example, boramidas versus boronic acids. This is basically the same plot, but niceified. And of course, we cannot get absolute yields, but we can actually get the peaks in the HPLC, and therefore we can figure out maybe there's no product because things were not soluble. Maybe there's no product because there was no conversion, or there's a lot of high conversion. So that's more or less how we think about them, not necessarily with a lot of precision, in the sense we want to more or less separate the different fractions and then look at them in the laser. What is super exciting and probably the most favorite slide in my life is the result of a closed loop, right? So this is an iteration of the closed loop of 40 reactions to make 40 laser derivatives in a single step double capping Suzuki coupling reaction. So we have a dihydrogenated core where there are 40 different ligands that are attached to it to come up with about 40 molecules that were carefully selected around a particular organic laser candidate where we're trying to minimize the lifetime, maximize the relative quantum yield around a particular color series. And we found already lasers that are better than the ones that we started from. These are being synthesized by CROs and by us and in scale. And then we're about to send them to Chihaya-Dachi. So we closed the loop with Chihaya-Dachi once, 4 years later. So self-driving labs, how fast they accelerate, depends, right? We're about to get ready to do this thing 24/7 every day, but this is kind of where we are today, and it's super exciting that hopefully a paper is in the market in the next few months, showing the results from devices coming out of these organic laser candidates, which of course I'm not showing you the structures yet. How much time do I have left, Tom? Just to calibrate myself.
You have about 20 to 30 minutes total, including questions, so it's up to you.
Okay, well, how much have I spent so far?
Let's say 20 more minutes.
20 more minutes. Yeah. Okay. Yeah. So plus question. Okay, that's perfect. I am on time. Okay, that's good. I want to calibrate myself. Okay. So for that, you need a lot of stuff, right? So I've been telling you that, in my opinion, this is all about multidisciplinarity. So in my lab, I have theoretical chemists, organic chemists, chemical engineers, you name it, computer scientists. So one of the things that we've been building is this open source package called ChemOS, right? That allows you to connect all of these things, right? Mostly the optimization aspect, right? So I'll be telling you a little bit about the optimization aspect. And then again, these remaining 20 minutes we will use to discuss a couple topics in that. So first of all, what do you need to optimize? What are the things that you need to think about in this space, right? So you need to think about optimization of continuous variables, and you want to maximize exploration and then balance it with exploitation, right? So for that, we built a package called Phoenix, where the code is online. I just have an advertisement. If anybody knows anybody, please. I know there's a big audience, and everyone's interested. I'm hiring a software engineer to professionalize and maintain these codes in my lab. We made an offer, but it was unsuccessful. So we started the hiring cycle again. So if anybody is in this room and is interested in being the software engineer for this code, please apply. The ad is going to be online soon again. Right now it's advertised internally at U of T. Bottom line, we have this software package called Phoenix that allows you to use Bayesian neural networks in the low data regime, the regime that Anat was telling you about, to build surrogate functions for the optimization function at hand, and then try to explore or exploit. This is a parameter lambda that we have in the model that allows you to explore or exploit more aggressively, and propose new experimental data points. That usually, if not all the time, has to be combined with Chimera. What is Chimera? Chimera is a Pareto multi-objective optimizer that we all need to kind of think about, right? We need to optimize one thing first, like yield. The second one is cost. The third one is function. Fourth is fluorescence. Fifth is this. Seventh. You want to optimize all of them in such a way that the optimizer picks your favorite one. And once it's in a particular threshold, then within the surface that contains that threshold, you move into the second variable and then into the third variable. And if you start failing, you can come back and hop into the previous more primitive or more important surfaces. So it is just shown here by these welded surfaces here. So we always put Phoenix and Chimera together, but we also now have Griffin, which was just accepted for publication, appeared in publication. And what Griffin is all about is of the relaxation of these categorical variables, which are choices, into continuous spaces, including the use of chemical descriptors, as I'll show you. But what is so exciting about Griffin is that now we can combine things like which ligand are you using, which catalyst, which solvent, or whatever, with how much of it, how much of that, how much of this, temperature, etc. So you can seamlessly combine categorical with continuous variables. And then by using multi-objective Pareto, you're almost there. But it's not enough. There's a lot of work, and I consider this a big subfield of chemistry right now, thinking about these different different objectives. For example, you may have a lot of computational data, but very little experimental data. How can you leverage the computational or very cheap characterization data with more expensive data? So for that, you want to have this kind of delta machine learning approach. So within the same context of our optimizers, we developed Gemini to do that. You also, this is an information that we got from Merck. Sometimes you don't want to have the most optimal thing. You want to have the most robust / optimal, right? You might be satisfied with a less optimal region, but that is more robust in terms of processing. This is very important, for example, for process chemists. In different factories, you will have slightly different procedures. So we invented Golem for that. That's already on the Chem archive, and you can actually look at the Golem. And finally, you need to benchmark with each other. So we prepared Olympus. The LabKing group also has another benchmarking tool that is pretty cool. But whichever tool you want to use, basically, they will allow you to compare these algorithms with other algorithms, right? So again, what I really like about Griffin is that you can deform the surface where you relax your variable, and you can deform it using descriptors. For example, if you know that the HOMO and the LUMO of your molecule are important, or these particular geometric parameters for a catalyst are important, etc., you might want to put them into the Griffin. And then this is an example of a combinatorial search of organic acceptors based on a library of non-fullerene acceptors for solar cells that we use computationally with Steven Lopez and Benjamin Sanchez-Lengeling in this quote-unquote old paper from 2017 in the journal Jeweled. So what we did is we took those and we threw them into Phoenix. And you see that Griffin combined, basically is about the state of the art with GPyOpt. It only requires about 11% of the space to find an optimal molecule within a particular threshold. You don't need to evaluate all of them. You will need to evaluate only 400 of the 4,000 roughly, in average. But now if you actually add and prune the descriptors that you know are going to be important for this particular molecule, for example, optoelectronic descriptors, then you can get another factor of 2 because now you involve the chemical knowledge. This is extremely important, as I will tell you about. If you know features or descriptors, for example, of phosphine ligands, or features or descriptors of boronates that we just heard about, or etc. If you know the descriptors for those molecules, you can put them into Griffin right away. Okay, so far Olympus it's already impressed in MLST. It has a page number. Sorry for not updating this slide. Olympus can only compare right now Phoenix versus all these continuous variable algorithms, but we want to expand Olympus to categorical variables and have categorical variable data sets so people can combine and extend and compare the different algorithms. Okay. So this paper, which by the way is also impressed in communications chemistry, I don't know if Jason already presented it or Matt, but this is a collaboration between the 3 groups. From my perspective, what matters here is that we used everything. We used Matt Sigman's mapping of the ligand space to pick the best possible categorical ligands to explore in these phosphines, and then Melody used Griffin Chimera and Phoenix to optimize the reaction conditions of this particular reaction and get a high yield as compared to humans by picking this categorical variable, say ligand, with a particular temperature, etc. Notice that here you want to maximize some variables, minimize some other variables, and all of that can be done with Chimera. So I think Chimera, Phoenix, Griffin are going to be very important. Now, do we lose creativity by doing this, right? Do we kind of have now become robots? And the answer is no. This is a great example, right? I told you about the emitter technology. We were in the 3rd generation. I'm even skipping the lasers because they are a different mechanism. They are coherent. But if you continue thinking about what will be the next generation emitters, there is something called hyperfluorescence that the company Qlux works on. I actually, for full disclosure, I actually have stock options in Qlux and collaborate with them. But there's even an extra dream, which will be to have molecules that have the triplet above the singlet. Turns out there were very early papers in the 60s and 70s that showed molecules that have this property. The problem with this property is that molecules then are not bright usually. The singlets will not have a big oscillator strength. So what we found were the first bright molecules in this class, okay? Molecules that have the particular cores that enable this, discovered by Piotr da Silva and others more or less around the same time in the literature, but by using a human-driven, human-in-the-loop driven virtual screening. This is led by Robert Police, but also Pascal, Cyril, and Gabe that moderated one of the previous sessions, allowed us to find the first molecules in class on this class that obviously you can imagine what we're trying to think about, how to scale up the building of this course, and then hopefully how a robot can completely decorate this quickly and explore the space very quickly. So really briefly, in the remaining 10 minutes or so that I have, let me tell you about something that appeared on ChemArchive yesterday for this talk, right? This is kind of was prepared for the VISTA symposium. So this is the first time I present this publicly, okay? Think about a good public transportation system. One of the reasons to move to Toronto from the US is you have a real, true, fantastic public transportation system. So inspired by it, we want to think about robotic synthesis, okay? So think about planning synthetic routes where you have pre-human modification and post-human modification, and in the middle you have a robotic synthesis scheme, or any order you want. But for example, you have this particular dihalogenated compound, which might have been prepared by Ramirez olefination and intramolecular Ullmann coupling to close the ring. And you might have this other convergent path, right, where you're actually doing a Suzuki coupling to do a secondary Suzuki coupling with it, okay? And this will be the synthetic scheme to come up with this molecule that will be very important, for example, as a chromophore or a drug, right? And then furthermore, as a nucleophilic aromatic substitution will be done by hand. So everything that has been done by hand is like walking to the subway. Everything that has been done in pink here was done in the subway. So you can think about walking to the subway, taking the subway, and walking out of the subway, like you will do in a good city like Toronto, right? So you need to have a quantifier of combined synthetic routes, okay? So synthetic accessibility scores are good, synthetic cost scores are good, but they are not necessarily what we need. So obviously we needed to create our own score, and we want to calculate the commute, right? What is the speed? That basically means the amount of material, the cost, how hard it is to carry out a step, okay? And therefore, we created this thing called the step score, which is basically, you can see here the formula. It contains cost, C, times T, right? Materials, M, right? And the number of components, Ni, right? So basically this formula, if you stare at it, it's very simple. It's just basically accounting. It's almost like an Excel formula, or how much does it take you to do something, of course, with this geometric mean. And then when you divide it by the number of steps to reach the number of targets, you end up with a number that we call the route score. That is usually has, it's in the value of the route scores are in the tens of thousands, so you will see log linear plots for it. But you can certainly take a drug-like compound and do route scores for it. And then the units of the route scores are there. Again, they have to do with the cost of actually making the molecule. And you can actually just plot the route score with respect to the yield and then pick a reaction based on what you want to waste or not waste in terms of human or robotic resources, right? So that's the tool that I want to tell you about, combined with the new directions, right? So, okay, so that's route score. This is actually disordered. Let me just tell you this route score and then come back, okay? Sorry, I was modifying my slides and this is disordered. So now, why am I so excited about route score? Remember, what I really want to do is make organic lasers, right? But now I want to expand the library of my organic laser to fragments that go beyond the fragments that I purchased in my robot, okay? So therefore, I'm going to allow my cool chemists to do nucleophilic aromatic substitutions and bookwells. So this is an example where we took 10 A, B, and C midaboronate type of blocks, and then built a library of about 3,500 candidate molecules, but that allows for the human pre and post modification costed by route score. Okay. But now we're going to use Chimera and Griffin. Okay, this is everything combined now, right? So I'm going to actually now computationally, having that route score, use Chimera and Griffin together with my calculated quantum chemistry data for the molecules in terms of the peak score. I have a score that tells me what is the color of the molecule, the desired wavelength. That's the first layer of Chimera. The second one will be the route score, how hard it is to synthesize it. The third one will be what is the spectral overlap between the absorption and the emission for the laser. And the fourth one, the fluorescence rate. So this is a concrete example of 4 different levels of Chimera that I'm very interested for an organic laser. And then I throw the optimizer at it with my computer. And I ask myself, what happens, right? So if you just optimize by the peak score and you say, well, I really want the best possible molecule, you will end up with this monster, very hard to synthesize. But now I'm going to compromise. I'm going to use Chimera, okay? And I'm going to optimize, including, excuse me, this is a monster. I apologize. Including the route score, I come up with this molecule that is easier to synthesize. Sorry. So this was the molecule that was very hard, and this is a molecule that is very easy. We pay a penalty on the peak score. We pay a penalty on the overlap. Okay. We also pay a penalty on the fluorescence rate, but at the same time, we have a molecule that is very easy to make. Okay. So that's an example of how you can combine all of these things together. Okay. So now I'm going to go back to the slide I had misplaced. I think also connected to the previous talk or other talks, it's just not, and Jensen as well, right? It's not enough to just do all of this at the level of black box. Like at the moment, in some sense, we have a black box in terms of what's his name's Bartosz Rybowski's prediction at the level of informatics of which reactions happen or not, or my Chimera, Griffin, etc., based on data and experiments. You need to go deeper. And Jason Heim probably told you about his very beautiful sampling. He has new auto-sampling tools that are amazing, combined with experimental tools that actually allow you to do real-time kinetics understanding. You can actually use database tools. This is a database tool led by Tobias Gensch that gave those passos, a collaboration between Matt Sigman and my group. I think he was mentioned in this conference before. It's called Kraken. Combined with our IACTA algorithm for finding mechanisms on the fly, which you can read in this paper. This is led by Cyril Lavin. We're getting more and more excited about doing mechanistic unraveling in the mid to high throughput, hopefully, zone of these reactions, right? To try to understand why a reaction didn't happen or it happened at the level of a molecule. And in this particular case, in the IACTA was able to find the mechanism of this Berkeley on total synthesis. So I invite you to check out that article. Okay? And in my remaining 2 or 3 minutes, let me tell you about the future. Okay. So this is what I think we should be thinking about, just to end this conference in a high note. I want you to think about what will the future look like, right? If now instead of having these liquid handling robots, I have a robot that picks up this glassware that has some tea here, which I will be drinking, and does exactly the same operation, okay? By mixing whatever was in this flask with this flask, right? And takes a syringe and like injects terbutyl lithium and picks up a schlenk and like opens a valve. Is this even possible? So we have this paper in Chemical Science where we did the 2-dimensional version of this. We created a data set called the Vector Lab Pix data set where we segmented. It's a beautiful story where Nessa Carson, for example, was one of our most favorite users. She sent us so many photos that she had been taking. So if you had the addiction of taking photos of your lab setup, send them to us and we'll annotate them and we'll put them in our database to do computer prediction. But not only that, I mean, this is how the 2D network looks like. This is exciting, right, people? So now we can actually predict, hopefully my robot, my video is working. It looks like it's like I will skip it. But I'm super excited that we just submitted this paper to a robotics conference. Now we are generating the three-dimensional version of this with cameras that are three-dimensionally sensitive. The problem with three-dimensional sensing, even state-of-the-art, is that transparent materials are really crappy, right? Because you get fake reflections, transmission over them, etc. So I'm very proud to brag that my lab, Haoping in my lab, has the state-of-the-art model, even better than NVIDIA's, for chemical glassware. That basically means very soon we'll be able to, by using a camera, perhaps rotating around an object a little bit, understanding that the transparent object is there, how much liquid is inside of it, and then calculate on kind of like very, very natural language-driven chemical synthesis using robotic arms. You can imagine the applications for this. And I just want to tell you, I think that's going to be some of the futuristic type of research that I want to think about in my laboratory. And with that, I'm just going to end thanking some of the people in my lab that did all this work. Tony Wu, Genia Bestfried, where is Genia, have been incredible at setting up the lab initially. I would say, needless to say, Cyril has been, instrumental in a lot of the computational tools. So is Gabe over here. And I could keep mentioning people, Robert Police, Matteo Aldeghi, etc., that have been just basically phenomenal in doing all of this work. So with that, I'm just gonna Gabe again. I don't know why I'm thanking Gabe twice or thrice, but I really wanna thank you all for your attention, and hopefully I still have some time for questions and answers. Thank you.
Thanks for the wonderful talk. We do have some time for questions, and I think there are a few in the chat. The first is an anonymous question. Says, hello, Alán, great talk. Given that there are so many optimization algorithms and schemes, as well as so many chemical variables involved in making the perfect functional material, how do you go about choosing which algorithms and variables you need?
Well, Anonymous, you have to know that we are thinking hard about that, and that's the reason we release Olympus. So at least in the case of Olympus, you can download it, add your data set, or use some of the data sets that we have fitted there and test which algorithm works best for your problem. Obviously, we want to add categorical variables there, but that's where the human comes in the loop comes along, right? You're going to need a human to have those taste of picking the algorithms and trial and error and so on. And that's where I also was talking about learning curves. The more we do this collectively, the more it's published, say in the journal Digital Discovery, which you should all send your papers to, then the more we learn collectively how to do this faster and better.
That makes sense. And again, congratulations on the journal position. I guess maybe a more philosophical question that's sort of related is, I'd be curious to hear your take on the role of the chemist in this futuristic sort of approach in lab. And I'm sure it's a question you get asked a lot.
Well, I'll tell you the answer. And I'm sorry it has been also published, but I'm going to try to come up with another answer that is not repetitive. But for those of you that haven't heard it, I am a Latin American. I like Latin American poetry. And I also like to play chess. You can find me in chess.com. Maybe we can fight each other in chess. But there is this beautiful poem about chess by Borges that says, who is the heart behind the god that moves the player, that moves the piece, that starts this game of dust and agonies, right? What a beautiful ending of a poem about chess. Well, if you think about that, the chess game is this kind of rule-based thing that we built, right? The chemical reactions have these rules, and we have an infinite space to explore. It's called chemical space. But, computers can be very good at it, but there's a human that needs to design the computer. There's a human that needs to design the rules of the game. This is a little bit different because every lab will be playing a different game of chess. So I also saw a screenshot with my spy Gabe of the first talk of the symposium of today about the Luddites, and how people were very worried about the rise of the factories. This is the same thing. People are worried about this type of technology. I think the only thing it will do, it will make the organic chemist more like a biologist. Biologists developed CRISPR. They developed mRNA technology, standing on the shoulder of giants of digitalization and automation. If they couldn't carry out so many experiments at once and store their data collectively and analyze it, the biologists and biochemists would not be where they are today. And we, the chemists, are in the Stone Ages compared to them. And the people in the audience in here are the ones that are going to transform organic chemistry and put it more like on par of a field that is ahead of us, like biology.
I think it's a great answer. Another question from Bo. Are you able to generate categorical experimental design space when doing surrogate modeling, or must we rely on pre-designed space and or enumerated data sets?
Yeah, of course it's possible. It's a good idea, but one could have a BAE for experimental conditions where you generate new ligands or new solvents or combination of solvents beyond what you originally envisioned with Griffin and Chimera and so on. That's a beautiful idea, but I don't think my lab has gone that far to try to implement a tool that does that, but I see it going there. And so I appreciate your futuristic vision on that. First, let's get the Chimera with the conditions and ligands that you already predefined working. But for doing it what you want, Paul, we might need to buy reagents, or we might need to pre-build them with subway maps, right? So like maybe we need to, the generative model might generate a ligand that we don't have, and therefore we need to make it in the hood. So I think to do what you want, there's a challenge of getting the right precursors or reactions or catalysts that you might not have in your lab. So you probably are always limited by what you have in shelves or you can order. But that's where I think combining the subway map with what you were talking about, Paul, might be very interesting. So thank you for that suggestion. I'm not there yet, but I see it. Yes, it's a good direction. Write a paper on that and send it to Digital Discovery. You are correct, Rajat. I forgot to say Digital Discovery is a sponsor of this conference. So even better, submit papers. You know, we're even sponsoring this conference, for God's sake. So send those papers. You will be delighted to see who's in our board very soon and who's going to handle your papers. I can't wait to disclose it.
Bo says, great point, thanks. Another fun type question is from Gilberto Enrique Fernandez, who wonders how much time you spend unclogging your dispensers.
Gilberto, I am the theoretician that runs the experimental lab. I think you want to ask this question directly to experimentalists in my lab. So if you shoot me a Twitter direct message, I can connect you with, say, Han Hao, or with Emily, or with Tony or Genia. They can certainly tell you about the woes that we have with our powder dispensers and the tricks that we're doing, and our new Metler Toledo machine that we have to dispense powders to complement the chem speed and all those nice experimental things that, as a main big enchilada PI, I don't know about.
That makes complete sense to me. Cool. I don't think there are any other questions in the chat. So with that, we can thank you again for the wonderful talk. And I think Rajat wants to take over from here.
Okay, thank you. I just want to say one last thing. Naveen has a question about molecular tinder. Naveen, we did have this molecular tinder for the Samsung project, but it's not available. It was just for the Samsung project many years ago, but you can imagine making it very quickly. It's just a voting interface that shows organic molecules to the synthetic organic chemist, and they vote yes, no, or maybe, and then you start tally that. So you can give it to an undergrad, and they can do it in a few weeks. But unfortunately, Naveen, we don't have that code available for anybody. And on that note, I'm going to shut up now. Yes.
Thanks. I actually missed that one. Okay, Rajat, I think you're muted. Rajat, you're muted.
Sorry, can you hear me now?
Yes.
Yeah. We can't have a better ending of this entire 6-day long conference, and I want to really thank to all of our speakers, all of our moderators, all of our student attendee, and if you allow me to have 5 more minutes, not for me, but on behalf of my team, so that I can acknowledge them, and I can also summarize. I would also like to summarize the entire conference for you, particularly those people who haven't attended the first day of the conference. So there is a chance that you might miss several information. So I feel that that would be a good idea to summarize whatever we have done so far. So, I mean, our speakers are actually our hero, because it is actually due to them that every day we have more than 500 attendees. Even in our worst days, we have nearly 550 attendees. So that's a huge number, given the fact that when we start, it's almost midnight in Asia, and very early morning in US. So it's mostly the case that when people from Asia tend to leave, then people from US tend to join. So 600 to on average 800 number, that's quite remarkable for us, particularly who never had organized any conference, and the entire credit and should go to the speakers. And in this entire lot of speakers, we have industry speakers. We have 9 industry speakers who actually came forward, and then they shared their insight, their tips from industry. And I hope that people from academia, they get a chance to know more about the industry research and how things are doing there, and what are the main differences between academia and industry. I would also like to highlight, as I was organizing this conference, I want to make sure that there is a healthy proportion between male and female speakers. So in this conference, we are delighted to have 11 female speakers who actually presented in the last 6 days, and I am incredibly thankful to them for their participation and for sharing their insight. Now, this was almost impossible to do without any sponsorship, and it might sounds very simple today, but when I first started to reach out to journals, people thought that this guy probably is crazy, and they are not wrong, because so for any postdoc to reach out to a big journal and asking that, hey, can you support us? But I'm really glad that they did, and it's their support which enables us to make this event free for all our attendees, because our main goal was to make this conference look like a virtual garden. Now, we understand that we can't serve you lobster, we can't serve you exotic wines, but definitely we can make sure that you attend the best talks across the world from the experts without paying a single dime. And all our sponsors make this possible. And I would like to highlight also Digital Discovery, the journal that Alán mentioned. They are also one of our sponsors. And definitely we received this sponsorship across different editorial houses like Cell Press, Thyme, Wiley, Nature, RSC, and also industry like Deep Matter. So I hope that this bonding will continue in years ahead. And most of the journal editors also participated in this event. Something that probably one of my biggest takeaway from this event. I'm really delighted to have them. They are really experienced, so it's a wonderful it's a wonderful learning experience, not only for me but also for the other students who actually participated alongside them. So thank you very much. We also have several external moderators, and some of them actually are assistant professors from different parts of the world. Today we have 2, and previously we also had 2, one from IISc and other from MIT. And we also have 2 industry representatives. They also participated in this conference, and I'm deeply thankful to them. We have 9 student moderators, and all of them has one thing in common. None of them are expert in machine learning. And this is basically is also true for the organization. None of us are expert in machine learning. So we attended this conference / organized this conference because you want to know what is the landscape. What is the current landscape look like? So on behalf of all student moderators, I would like to say thank to all our speakers and our sponsors. And we also have a healthy proportion of female moderators who participated during this event. And I think I definitely would like to single out this 5%. Without their help, this event would not have been possible. So if may I ask them to unmute themselves and open their video so that other people can see them. So Shinjini Bhattacharya. Shinjini is currently the first year graduate student, and this was organized based on their seniority level. So she is the junior most member in this lot. She started her PhD probably 8 or 9 months ago, and from her enthusiasm, you can see that, I mean, how much she was involved in this entire process. And I can't imagine that, our Twitter handles and, going through breaks, all those, big banners putting and even contacting several key people. She played a really invaluable role, and so do Lalita. Lalita actually just about to graduate. She is going to start her new position at UCSD, and just probably 10 or 15 days before her defense. I mean, I can't imagine that how much energy and how much time she had actually put in the recent few weeks on this particular program. I'm also thankful to Kali Shankar. Kali Shankar is currently an Alexander von Humboldt Fellow under the professorship of under the guidance of Professor Alexander Aul, and he also played a very important role time to time. And also Dr. Shoumen Ghosh, who is currently in India, and Shoumen is going to start his new postdoc position at PNL laboratory in US. But while he's in India, it's more than midnight. I guess it's already past midnight. He's still there, and he attended most of the talks, even moderated talks. So I'm really thankful to Showman. But the one person who actually stood out among everyone, I think that's our IT specialist, Anirudh Babbar. And both myself and Anirudh started working on this project 9 months ago. And I think there are times that, we felt that we should leave everything and go for a break. No way that this is possible. But I think Anirudh and his team, especially Think and Code, they actually worked tirelessly for last several months, making this event possible. All the graphics that you see and all the website, it's entirely their creation. And I'd like to thank Anirudh and his team for this service. And it was not possible without you, the audience. So please send your review and please write us how you think we can make this even better. Because one thing I can promise you, VISTA is here to stay. So we are going to organize future events, and for that we need to know what you feel and how you think we can make this even better. And with that, I would like to conclude this symposium. It's a great honor to have all of you, and I hope that we'll see again soon, hopefully next year for sure.
Good job, Rajat.
Bye. Take care.
Great job, Rajat.
Awesome.
Okay, the chat. And I will look at the chat because there are a lot of messages there.
I think I lost it. Oh, it's on my other screen. Stop share. Yes.
Rajat, please don't close this conference. We are getting some really nice feedback on the chat as well. Huh?
Okay.
We can save the chat on this.
have taken a backup of this chat.